On June 30th, 1908, near the Podkamennaya Tunguska River in central Siberia, a cosmic body exploded in the atmosphere. The airburst flattened roughly 2,000 square kilometers of forest, tens of millions of trees. It left no conventional crater because the object broke apart above ground, transferring its energy into air, heat, and shockwaves. Tunguska was the largest cosmic impact witnessed by modern humans. It proved that a space object need not strike Earth intact to devastate the surface. At about 7:15 that morning, the sky flashed brighter than the sun. Heat swept across the taiga forest. Pressure knocked people down and tore through the forest. The trees became the event's physical record. Trunks laid outward from the blast region, while some near the center remained standing, stripped bare. Tunguska is not mysterious because nothing is known. It is mysterious because the surviving evidence is powerful, incomplete, and separated from the event by distance and time. The best-known account came from Semen Borisovich Semenov at Vanavara. He recalled the northern sky seeming to split, a wave of heat reaching him and a powerful blow throwing him from where he sat by his house. Other reports described a bright object, flames or glowing color, thunder-like detonations, broken windows, damaged camps, injuries, and reindeer losses. These accounts preserve the human scale of the disaster, but they are not real-time transcripts. Expedition member E. L. Krinov recorded Semenov's testimony in January 1930, more than 21 years after the explosion. Memory changes, translation compresses meaning. Estimates of direction and sequence can drift. The surviving record is also unequal. Russian-language testimony was more likely to enter scientific archives than the experiences of Evenki communities nearer the blast. The responsible conclusion is therefore narrow. A sparsely documented human landscape experienced an extraordinary event whose broad pattern is consistent across many reports, even when individual details cannot be treated like instrument readings. The forest preserved the clearest physical signature. Later surveys mapped trees felled across roughly 2,000 to 2,200 square kilometers. Their trunks did not point randomly. The broad pattern radiated away from the blast region, while local variations recorded terrain, tree strength, and the complex movement of the shockwave. Near the center, some stripped trunks remained standing, a result consistent with pressure arriving more nearly from above. Together, the fallen and standing trees became a giant instrument after the fact. Researchers used them to test trajectories, burst heights, and energy releases. The famous figure of 80 million trees also needs discipline. Nobody counted every trunk. It is a scale estimate reconstructed from damaged area and forest density, and other summaries use lower totals. The honest phrasing is tens of millions of trees, often estimated near 80 million. Fire and thermal effects were reported, but weather, insects, regrowth, and later human activity changed the site long before it could be surveyed systematically. Science reached the blast zone late. War, revolution, civil conflict, and the region's remoteness delayed sustained investigation. Leonid Kulik, a mineralogist and meteorite specialist, found old reports and became convinced that a major fall deserved study. He led reconnaissance in the early 1920s, but did not reach the devastated forest until 1927. River travel, winter tracks, bogs, and local guides stood between the railway and the center. Kulik expected a crater and recoverable meteorite iron. Instead, he found the immense treefall zone and no obvious impact bowl. His teams mapped, photographed, questioned witnesses, and searched the wetlands. The strongest surviving expedition photographs date mainly from 1929 and 1930. They document damage still visible 2 decades later. They are not images of the explosion itself. The expedition record transformed a remote story into a scientific problem, but the missing 19 years could never be restored. The absent crater is not a contradiction. It is one of the strongest clues to an atmospheric airburst. A cosmic body enters the atmosphere at enormous speed, carrying kinetic energy in its motion. As the air thickens, pressure builds around the body faster than weak material can withstand. Cracks propagate, fragments spread, and an expanding cloud transfers energy into the surrounding air. The result is not a neat detonation at one mathematical point, but a rapidly evolving column of energy deposition. Shock waves and thermal radiation can devastate the surface, while the main body never reaches the ground intact. Modern summaries often place the original object somewhere around 50 to 100 meters across, with the principal burst several kilometers above the ground. A NASA workshop studied representative stony asteroid cases near 50 to 80 meters, roughly 10 kilometers high, and in the range of 10 to 20 megatons. Those are models, not measurements made in 1908. Change the object's speed, angle, composition, strength, or breakup sequence, and the reconstructed answer changes. Lake Checo has been proposed as a crater made by a surviving fragment, but that claim remains disputed. Samples from the region have produced candidate particles and unusual rocks, yet contamination and uncertain collection histories limit what any single specimen can prove. No confirmed conventional main body crater or large impactor has been established. Tunguska damaged Earth because the object's energy reached the surface, not because an intact rock had to strike it. For decades, the missing crater and missing main body kept several explanations alive. A comet once seemed attractive because an icy, fragile body might disappear high in the atmosphere. Modern simulations show that a weak, stony asteroid can also fragment completely and reproduce the broad scale of the blast. Most current scientific summaries favor an asteroid, but composition, path, speed, strength, yield, and exact burst height remain uncertain. Published trajectories differ because witnesses and tree fall patterns constrain the path imperfectly. Microscopic particles may be suggestive without becoming a unique fingerprint. Scientific uncertainty does not make every story equally plausible. It means the leading explanation still carries error bars. The event also seemed to echo far beyond Siberia. Around June 30th through July 2nd, observers across parts of Europe and Western Eurasia reported unusually bright nights. Fine material or water high in the atmosphere may have scattered sunlight after local sunset. Noctilucent cloud processes have also been discussed. The reports are historically real, but their exact mechanism and connection to Tunguska remain debated. The broad scientific conclusion is clear. A natural cosmic body entered Earth's atmosphere and released most of its energy in an airburst over central Siberia. The 2013 Chelyabinsk event later showed, on cameras and instruments, how a much smaller body could fragment in the atmosphere and send a damaging shock wave to the ground. It did not solve Tunguska, but it made the physics tangible. Today, Tunguska remains a central test case for planetary defense because it shows that the atmosphere itself can become the impact site. So what really happened in 1908? Almost certainly, an asteroid-sized body broke apart several kilometers above the taiga forest and converted its motion into heat and blast. The witnesses preserved the human experience, the forest recorded the violence, Kulik preserved the aftermath, and the missing crater preserved the answer. The decisive collision happened in the air.